I'm going to share my screen. If I can get it to share here, double click, give it to me. Okay. And let's go. Okay. It says I'm sharing. I'm going to move some things around here. Hopefully I'm not having any internet issues or anything like that. Just to be sure, before we get going, you guys can hear me. You can see my PowerPoint and you're ready to go. I got a yes, a yes, a yes, a yes. I'm seeing some yeses. All right. Like I said, I got a cold tonight, so if I start coughing or anything, I'll drink some water. If internet goes out or something like that, you let me know and I can repeat anything. Okay. Tonight we're doing Boolean programming. You're going to be filling out a lecture worksheet. It's going to be a little redundant because you already did the homework. This week, the quizzes on the Boolean, or next week when you take the quizzes, are usually pretty good. People usually like the Boolean. It seems kind of logical to them. And we will go over it and you'll be like, some of you are like already getting it. You'll be like, wow, this is really boring. But and then others will be like, oh yeah, this is kind of cool. I get it. But I'll be recording the lecture and you can watch it. You're filling out your pink sheets. What we're doing is we're doing ands, nands, ors, nors, and nots, the pictorial representation of them, the Boolean equations of those and how they are equivalent to ladder logic, explain how logic gates work. We'll draw the logic symbol, construct a truth table, and state the Boolean equations for various gates. So we do a little Boolean programming, okay? Before we do that, we are going to start with the model, the last week's review. So we did a Siemens setup. And what I have right here is I've launched my TIA portal and I'm in the middle of a download, all right? And I've got my little unit right here, by the way. And I was in the middle of a download. It kind of looks like yours. And when I clicked, you know, start search download, it says assign an IP address. Would I like to assign the IP address? I'm going to click yes on this. And the beauty of this is that you don't need to go into your adapter settings. Remember when we were down here on network and give it a static IP and all this? You don't have to do that. This added the static IP address, and then it sets the network up for you. It is downloading. Sometimes when it downloads, you get a little red up here. A little issue is red, an error. And if there's an issue that's red and that you can correct, it will give you usually options. And if you collect all the red, you will get a load. Okay, I'm going to continue without synchronization. I don't know. That's here. I got a stop module. I got some things going on here. So what I got to do is I need to stop all, and now I get the load. So once you get the load, you can then go ahead and load it up. I've got a synchronization error. I must have a firmware issue with my PLC, but let's just see what happens when I click finish. Let's see. Okay, says it's finished. I don't know why I'm not online here, but I really want it to be. If I click my eyeglasses right here, I'm going to go and it's going to slowly but surely put me online here. There it is. Okay. So I am online. I'm in the run mode. I don't really need this screen up. All right. Sometimes when you're running or you're trying to do something and it's not working, it's because you might have stopped the processor. And so when you push the inputs, it doesn't update the outputs. So another way to do it, this is like a VCR button right here, like a start button and a stop button. You could start and stop the processor right here. So you could do that on the SLC 500 as well, just with a key, or put it, your remote program versus run. So first of all, scale of 1 to 10, do you agree you have to be in run mode in order for it to process logic? Got to be in run mode. Yeah, sometimes it won't work. All right, next. Over here, what we had was, I'm just going to close this. I don't need this over here, okay? Typically, I just run everything now off of this screen and up here. When you went and set this up, you added an analog signal board. Okay, the analog signal board is buried underneath here. Okay, this does do analog. You don't need to add that anymore when you set it up, because even though it's there, we're not using it. So it will just help you set this up, you know, a little bit faster, okay? So a couple of other things about the screen right here. When I go the lower left-hand corner here, I can click my portal view, and this kind of kicks over to my setup. And if I pick the project view, it kicks over to my program. This is where I'm programming. Portal view is where I set up. And when I added a new device, remember that's what we did here. We did the CPU, we did the 1214 AC/DC relay. I think most of us had 40s where you clicked it and then it pulled up a revision level and all this. So, and then you just clicked add. So that was how you added the CPU. You could add an HMI, you know, you can add other systems here. It's all part of this software. Whereas in Allen Bradley, you need RS links for the communication. You need a SLC 500 or 5000 software. You need connected components. You need factory talk view. You need everything, this and this and this. Siemens, it's just all on one right here. And once again, project view versus portal view that I'm clicking here is how you go and set it up. So far, everybody, scale of 1 to 10, does that seem to make like it makes sense to you of how to navigate between the two? Yeah, you're going to spend a lot of time right here on this page right here. If I click my devices and networks here, see it spins for a little bit and then it pops up. I got some stuff going on here. See all this stuff I got going right here? I'm gonna kick that down. This is my PLC. When I add HMIs and stuff like that, this will show me the network, because this little green right here will be connected to the green of the HMI or the green of the next PLC, the green of the VFD or whatever like that. It kind of shows you pictorially your little network there. I've got a PLC. That's what we're doing right here. I don't need to worry about the device configuration or diagnostics. We can get into that later. The big thing that you need to define, and you'll get used to looking for it over here on the browser, is the program blocks. And it was called the main OB right here, main OB, okay? And the main OB is where you're programming, okay? Another thing, another popular selection over here is going to be PLC tags, okay? So once again, when I show all tags, it's going to pop up like this for my tags. Now, what's cool about this is it's pretty smart. So I'm gonna make a tag name right here, and I'm gonna call it switch 1, and I'm gonna click enter, and notice it made it I 0.0. It gave me my address. I do switch 2, switch 3, switch 4. Notice it is pretty darn smart. It's automatically incrementing my addresses to the next switch, okay? And the way that I've got it here is I've got my switch here. There's my 0-bit, my 1-bit, my 2-bit, my 3-bit. So these are my switches like this. It's addressing them for me. But now if you want to then go like this to light 1, notice it made it an input. It's not that smart. What you could do though is come right here and you notice that the outputs are cues, and the first one was 0.0. Click. Now I've switched over to, you know, light 1 is a cue. It's on the 0-bit. And if I come right here and I type light 2, light 3, light 4, etc., notice it is changing the address and incrementing them for me. So it's kind of doing the addressing for me, okay? So that's where I'm gonna take you'll get used to making your tags here. In the description will match up to the addressing. So this is similar to the data table and the SLC 500. So on a scale of 1 to 10, do you see how these tags are generated, I's and Q's? How you feeling about this? It's a little bit different. It's tag-based programming where you give it a name and then you assign it an address. On the SLC 500, you had an address and you gave it a name. Slightly different. Name, address, address, name. That's how you look at it. If I go back to my main OB, I haven't programmed anything yet. I notice I'm still online. I'm orange here and I'm orange here. So the offline and the online programs are the same. If I come down here and I drag in a contact right here, notice that this is no longer orange because I've made a change. And I'm going to go ahead and drag in an output here. If I want to figure out what this, I can just double click it right here. And because I made all those tags, I can pick switch one. And if I come over here, give it a second, it's kind of slow. And I double click here, I can name this light one, okay? Now I've made a change. All I got to do is click the download button here again. And it's going to just pump it all down. And that's like doing an online edit, okay? You don't have to go offline, make this change, then go online and do it. You just make the change and click download again, and then there it is. Now I come over here and I click my switch. I'm just clicking it over here. And notice it does read pretty fast of how fast that it reads it, okay? Another couple things. When I click into my tags, or I click into my main, or I click into some of these things, it takes a little while to load. But once it's loaded, look down here. See these windows down here? These windows, once I clicked on them once, they're generated. So if I click on this PLC tags, it pops it up, and I go my main OB, PLC tags. It's a really quick scroll back between these. Here's my devices networks because I loaded that up early. So if you want to jump between the main and the PLC tags and everything, you can do it all over here in the browser. Or once you've done it once, it can populate down here. So scale of 1 to 10, does that make sense about navigating either through the browser, or once you've done it once, it's down here and you can do it, okay? So when you get going, I think you're going to want to find that you're going to come and you're going to, because we did good practice of creating a map, an IO map. You're used to doing that ahead of time. That if you create your IO map and you come over here and you show all tags, and then you create your tags, then when you go to programming, they are available. Now, when you're adding more rungs, let's say you want another rung. You got two options. You can name this network right here, basic circuit. I don't know, whatever this is, basic circuit. That's how you do your rung comments. Now, if you want to add more down here, you can drag this down to here like this, and you can add, another rung. And if I go here and I just type SWI, see how it pops up with switch 2. And if I come over here and I can click that little, I can click and find it, or I can just start typing light LI, and there it is right there. So that's one way to add lots. You can put it all in network 1, or you can come down here in network 2 and do another basic circuit, however you're grouping your stuff. And you could put that down here like this. And once again, if I wanted to do this, I just start typing S and it pops up. And if I come here and I just start type, if I don't know what I called everything, I can go here, I can click there and do it, or I can just type L, there it is, light 3, okay? And once again, I've made some changes. Boom, click the download button and it compiles it. In fact, I want to overwrite the main, yes. And then it might take a second, and then there's my online changes. I'm ready to go. Now down here, I got a lot of nice blues. That's good. Everything's really good and happy. I can have warnings, but I can't have errors. Okay. If I do have an error, I'm gonna make an error for you. Let's see if I can make an error. I don't know. I'll go like this, and I'm gonna put a parallel in here, and I can close it up. I can either drag this here, or I can just drag this up to here to close it up. Okay. I'm gonna click the download, and it's gonna download, and there's gonna be an error because I didn't get that. So it's got a problem here, and it says 1 error, 1 warnings. And if I click the green button right here, let's see what it does. It takes me right to where the problem is. Okay, so if you've got a problem down here and it's red, click that green arrow and it takes you right to here, which obviously this must be switch 4 or something. I can try and download it again, and it'll take it this time. I want to overwrite it, yes. And it just says it'll take some time. It really won't take that much time. And now I'm orange and orange again. They match up. My offline and my online match. So on a scale of 1 to 10, does this seem like you're going to be able to learn to navigate through this pretty darn fast? I think you're going to learn to really pound through this Siemens really fast, the way that you can get online with logic, make your, especially if you make all your tags ahead of time. Okay, so that was kind of the little bit of the review for that. Okay, we talked about the main OBs bottom. So remember, when this is orange, this is the online, and this is orange right here, the offline. When they match, you know, you're monitoring right here. That was that little eyeglasses. You know, your online and your offline match. That's a good thing. You can switch windows. We did that. We did project versus portal. We did the download. You click that. Anything needing action, you got to take care of. So if you get a red button like stop the controller or stop it, you might have to do that. I have to click on run in order to select the monitor icon. Yeah, if you want the monitor icon, you know, I'll say take a look at it. If you're not clicked into this rung, you can't get this. But if you just click into here, then this will pop up, and then you can take a look at the monitoring. And you'll want to monitor. You want to push the button and see what's happening. We did forcing. Forcing was just like the slip kind of, except the data table wasn't there. You had to kind of make the data table to do the forcing. So it was a little more, it was one more step that you want to force something on, you just don't fat finger a one. You got to create the table to then fat finger the one. You know, that's 2 steps. That must mean you did it on purpose or made it a legitimate mistake. So does everybody understand how to force something on here? You have to make a forcing table. One more step. Scale of 1 to 10. How are we feeling about that? Yeah, yes, or 10, yeah. You don't force things on very often, but you do. I had some students working on their capstone for the SLIC 500, and they got a light that just wasn't going on, and I said, well, force it on. So when they went in the force table SLIC 100 to put a 1 in it, enable, the light didn't come on. You know, the wiring looked good, the light looked good. I don't know what it was. They just moved to a different output. But you know, that's way it was really easy doing the SLIC. This is just one more step. I/O connections. So inputs are addressed as I. That makes sense. I. Remember, it's not 1. It's hard to, you know, you do mix up an I and a 1 once in a while, but this isn't bad. I. And outputs are Q, which will minimize the Q's and the mixing up a Q and an O. So I's and Q's. These are fixed PLCs. Have 8 inputs, 0.0 up to 0.1, 0.2, all the way up to 0.7. And then there's 6 more. It's binary. So it's only got it's octal. It only uses numbers 0 to 7. And then it starts over again. So after 0.7, it goes to 1.0, 1.1, 1.2, all the way up to 1.5. So they're grouped octally in bits of 8. So what does that mean exactly? And you'll get into this a lot in the PLCs. In binary, there's only 2 numbers. There's 0, 1. When you reach 1, you put a 0 on the end and put a 1 in front of it. 1, 1. Put a 0 here, a 0 here, and a 1. 1, 0, 1. 1, 1, 1. 1, 0, 0, 0. So that's how you would count binary. We go 0, 1, 2, 3, up to 9. When you run out of numbers, you put a 0 and you put a 1 there, 11, and you keep going all the way up to 19. When you run out of it, you go, 0, put a 2 there. That's how you count base 10. So octally, you go 0, 1, 2 up to 7. And there you go, start it over, 1, 1, 1, 2, all the way up to 1, 7. If you had to start over, it'd be 2, 1, like that. So it just depends on how many numbers you get to use. This is binary, is you have 0s and 1s. Base 10, or what we use decimal, 0 to 9. This is octal, 0 to 7. Does this concept of different numbering systems on a scale of 1 to 10 make sense to you? How are you feeling about this on a scale of 1 to 10? A little bit? I mean, if you had a 3, I don't know why you'd have 3, but you'd go 0, 1, 2. That's all you had was 3 numbers, 0, 1, 2. The next number is 10. And then 1, 1, 1, 2. You know, the next number is 2, 20, 21, 20, like that. You know, it's depending on how many numbers you're used to having 0 to 9 as your numbers. All right. But there are 10 outputs. Once again, they're grouped by 8s, 0, 0.0, 0.1, all up to 0.7, and then 1.0, 1.1. Up to, there's 10 outputs. Outputs 0 to 0 have a voltage common. Outputs 5 to 1 point have a common. This is confusing. Let's just look at this to be sure that you understand what's going on. So when I look at my controller right here, in all I see is my outputs. This says .0, you probably can't see it, .1, .2, .3, .4, .5, .6, .7, and then it starts over. .0, .1, .2, .3, .4, .5. So these are grouped by 8s. Now, same with my outputs, .0, .1, .2, all the way up to .7. And then the second byte is .0, .1. So they've got them grouped by 8s. Now, what's kind of confusing here is when I look at my relay outputs, and I'll see if I can, I don't know if I can get this quite good enough, but you'll have to take a look at it and I'll draw it for you. This says 1L. That means your line. This says 2L, but it's got 0.0, 0.1, 0.2, 0.3, 0.4, and then 0.5, 0.6, 0.7, and then it starts over at 0.0, 0.1. Okay, what does that mean? Well, here's what that means. We're going to take a look at our wiring right here. Here's the wiring harness for this. And it's similar that we get our freebies where we can run the voltage here and we can run the ground here. Okay, source and sink the output modules. All right. But now when we look at the input modules, you see that the first byte is right here. Okay. And it is 0 to 7. There's 8 bits is a byte. Okay. The second one is right here, but it stops. If we had more, it'd be 1.6, 1.7. The second word is actually right here, or the second byte. That would be my full word, but it's not full. We do not complete that byte. It's even though it's grouped in 8s, we're not using the last ones. And so when it says, a couple of push buttons or whatever, you're going to throw those onto here. I don't even know what I got, a 2-wire prox. You wanted to put a 2-wire prox on here, whatever you're putting on there, right? A 2-wire photo, by the way, might look something like this with arrows on it. That might be that there's a wave there. And once again, these would all be coming back to my common. All right. Same as what we did for the slick, essentially. Scale of 1 to 10, does this kind of make sense? The addressing and the wiring of inputs. You'll be able to hook up. Okay. The outputs are a little bit weird. Here you go. Ready? The output is organized by 8s again. So if I look at this, Q7, this is my first byte, 0.0 all the way to 0.7. And then if I had a second one, it'd be 1.2, 3, 4, 5, 6, 7. This would be the second. A 3-position selector switch. Hang on. Did it want that? A 3-position selector switch. I'm sorry. It would go like this. We could put it here, and we could put this in the middle like this, and then it would jump like that. So that selector switch would be in the middle. It would be off, and it would be selected left or right, up or down. That ring a bell to you? Look familiar? Good. All right. So now we're going once again to my outputs. And remember, they're grouped by 8, but we only have 10. So the rest of this byte is not available to us for addressing. Okay. But it does go from Q0 up to Q.7. But now what gets a little more confusing is the syncing of them. The sync is by groups of 5. So the first sync is right here. It's 1L syncs up to Q.4. 2L syncs the next group of 5. So the problem is the sync, or the sourcing, sorry, the sourcing 1L and 2L overlap and run over the first byte because they're grouped by 5, but the byte is 8 long, which could end up being a little confusing. This 2L right here, therefore, needs voltage running to it, similar to what we had before, but it's a group of 5 that overflows the actual byte that we're using going up to 0.7. Kind of crazy. And what we're doing on here, a couple of solenoids, 1 solenoid, 2 solenoid, a light, you know, whatever you had going on here, right? And then these things we're going to get jumped back to white, right? So that was going to be the way that we we're going to hook up our outputs. So scale of 1 to 10, does that seem to make sense? The way that you are hooking them up and addressing and stuff for the outputs? Oh, you said, is there a deeper reason why they did that? That came through the screen so fast that it got bumped off. I didn't see it. I don't think there's a really deeper reason. They just had 10 outputs and they cut them in half and sourced them that way. But it's basically Siemens. Is there a deeper reason why they did some outputs? Doesn't make sense in face value. Yeah, not necessarily. It just, you know, you see some odd stuff on your controllers out there. So when you're wiring up the controllers, the moral of the story is flip that cover open and see where the 1L and the 2L are and be sure that you're running your connections, you know, where they should be. Because in the real world, there's no banana jacks like that, okay? Another couple things. When I click this switch on, it reads the inputs here. So you still want to check to be sure that when you're pushing the button or clicking the switch or whatever you're doing, that you are getting the correct address to come on here, .3 or .7 or whatever. And if your program is not addressed to match up to that, it won't work. Same thing when it turns on this output, you want to be sure that you have the device hooked to the correct output, okay? Now here's another thing. These are what we have here. It's AC-DC relay. So this is powered by AC. It has DC inputs and relay outputs. That's the way this unit has. DC inputs. Well, our issue is we are using a training board that we've repurposed. And we already know on our training board, because we have all these 131 components, that we use AC. So you cannot run AC into this input module because it's a DC input module. That's what this is. So really what we've got going here, when you push this button, by the way, and this is not truly what we've got going here, it doesn't matter. What we got is when you push this button, we turn on a control relay. That's the way that we've got it. And then the contact from that control relay is what is wired into that input. So when you push the button and you hear all this clicking going on your on your training station, if you were to look on the back of the training station, look around it, you will see a bank of little ice cube relays. And that's what they're doing. They are taking their AC relays and they're just closing a DC contact, because the contacts here, they're DC contacts. Does that make sense to you? Why you're hearing the click? Scale of 1 to 10 of how you can turn on an AC relay and just wire the contact from it, because the contact isn't AC or DC. It doesn't care. Wire that into the input. Now the outputs here, they're relay. So my 1L and 2L, I could wire it, whatever. I could wire 12 volts DC, 24 volts DC, 120 VAC, 240 VAC. I can wire whatever I want in there, and they're just a contact that's closing. So that works fine here with our devices. So that is the I/O of the trainer. Okay. AC DC. We were using DC. That's what I said. Gave an example of how that works. Online editing, I showed you that the browser shows if online and offline are different, depends on if it's orange and orange. Review the quiz. The quiz was pretty good, a lot of good scores. We did a little quiz that looked like this. I think here it is. You were doing 3 starters to be wired. People got kind of creative. It was fine. You know, I was having fun with it, grading them. But basically what I did is I showed a CRM right here, a master control relay. And I put it like there just to indicate that there's power. And what I did is I closed line 1, and then I closed the neutral over here, right? Between these, line 1, line 2. And therefore, everything down here was kind of dead until I hit the CRM. And it was a 3-start station, so it looked like I did an on and off, an on and an off, an on and an off, and then I had an all stop. Here I put all my overloads. I just hardwired them into here, but a lot of people just did a total of 3 inputs for overload 1, overload 2, overload 3. Yeah, I'm fine with it. But then I had my all stop, which was normally closed. I just put it on every one. I put my overload on all of them because I had them all wired. But if you did it the other way, you would just have overload 1, overload 2, overload 3, overload 1, overload 2, overload 3, overload 1, overload 2, overload 3. I was fine with that. You had your on. What I need in here then would have been an off button for each one of these. So I got this turns it on, this turns it on, this turns it on. So this needs, it's off. Here's my other off, and here's my other off. So I could have added my off. And once again, it could be on either side of this, but so I would have had each station's individual off. And then here, I'm using fictional memory. So if you wanted to throw your aux in here, you could have, you know, thrown it in here somewhere to do some monitoring and put a light on, put 3 more lights out here or something, so that if this 1M was on, you know, we knew that it was on because the auxiliary contact was monitoring it. Could maybe master bit, didn't need it, but a lot of people put the master bit, which I thought was great. You know, you just had a rung that started, and if the master stopped or any of the overloads went down, the master bit went down, and the master bit was on each rung. That wasn't bad, you know. You know, just a few different ways to do this, but overall, generally pretty good. So I put my overloads on the master since yeah, some people did that. I'd have to take a look at why you missed a point or a point here, a point 2. You know, there was some weird things, like people made mistakes, like they put their overloads up here and they were shown as normally open. You know, I don't know if that was you or that, you know, they just had some random weird errors with the wiring. You know, that wouldn't have done it. But a lot of people just did have like a master bit here where the overloads in the all stop controlled that bit. You know, and that was fine. So we can take a look at it. You're not sure what you missed next time, but yeah, generally pretty good. All right. So as I described that, everything, does all this seem to make sense to you? Scale of 1 to 10, most of it. You know, different options here, different ways to do it. Master bits, overloads. Yeah. Okay. I think so. They were pretty good. All right. Now, we are doing Boolean programming, Boolean logic. So here we go. I'm getting cough drops. I'm getting hoarse already. Binary state. The binary state is 1 and 0. That's what we've been looking at data table 1 and 0. On, off, open, close, true, false, high, low. Doesn't matter, you know, how you want to say it, that you're just thinking about something on or off. It's got 2 states. All right. We've been doing a lot of that. When you look at a logic gate, the logic gate is examining, I guess, those 2 binary states. So a logical and, if you think about turning your high beams on, you would have to turn on your light switch, and if you want to stay on, you'd have to hit the high beam switch, where you're like, okay, that's a square box right there. You're thinking, oh, I know what's inside of that and right there, light switch and high beam switch. You're thinking this, light and high beam turns on, my not the headlights. You're thinking like I got a series ladder logic in there. That's kind of what you're thinking is going on in here, right? Well, it's not. You know, ladder logic is not the way things are programmed. It's just a way of presenting logic. This box right here, that's an and, you've been trained in your mind to see it as ladder logic. But if you're a straight coder, somebody who was just a computer programmer, they've never seen ladder logic. We just kind of made it available to you. What's going on inside of here? Yeah, this is kind of going on inside of there, but it's just logic. It's not actually ladder logic. Or if you open the passenger door, or if you hit the switch up on the light, it'll turn on the light, the dome light. Excuse me. You're thinking over ladder logic. Not really. Yes, but no. The AND gate. Excuse me. Is a device with 2 or more inputs and 1 output. So we did this with ladder logic, where you had to have both A and B pressed to get the Y. There's no ladder logic here. It's just this symbol, a 2 input AND gate. All right. Does this make sense to you that this replaces the series circuit that you've been trained in your mind? It's just a gate. Scale of 1 to 10. Can you wrap your mind around this? I know you did taken a couple years to learn ladder logic to realize that ladder logic's not really the way that logic was developed. It was kind of developed backwards to that, if you would have it. The OR. Here's the truth table once again. All you had to do was push A or B. So, you know, you're not pushing either one of them, you're getting 0, but this or this, you could push them both, and that would do it. Once again, there's no ladder logic. It's just this symbol, all right? This is and or logic, examples 1 and 2. What is that? Let's see what we got going here. Yeah, maybe I got it right here. Let me get a piece of paper. Hang on, right here. All right. I'm coming. All right. So we got PB1 and PB2. So I'm going with, you know, this is our little cheat sheet right here. We've done our ands and our ors. All right. So I got PB1 and PB2. And if I push both of these, if I put a 1 here and a 1 here, I'm going to get a 1 on this side of it. Okay, that's, you're thinking like this is ladder logic. Or PB2 and PB4. So now my OR gate is like this. So I'm coming here again. I got PB2 and PB3. So I need a 1 here, or I need a 1 here. How do I get, I showed you one way to get a 1 here is push both of these. Or if I get a 1 here and a 1 here, I get a 1 there. So even if this was a 0, I'd get a 1 here and 0 there. It's an OR, and it would give me a 1. Okay, so that's showing you how you can get PB1 and PB2 or PB2 and PB3. The ORs have the curve back. The ANDs are straight right there. First one here, scale of 1 to 10. How you feel about it? Yeah, I know you did it for the homework already. I know, a little bit redundant. I know. That's good practice though. What do I got here? I got PB1 and PB2. Okay, and PB3 or 4. So if I come right here and I make an and I go this and this and this, right? I've got this and this and this. The third condition, by the way, is an OR, and that's PB3 or PB4. So I got this and this and this, or PB5. PB5 gives me light 1. Okay. So it says OR. So if I had a 0 here and I push this button 1, I get a 1 there because it's an OR. If this was 0, I need a 1 up here. How am I gonna get a 1 here? Well, I got to push this, I got to push that, and I got to push one of these. Let's say it was 1, 0. It's an OR, would give me a 1. 1 and 1 and 1 gives me a 1. An OR gives me a 1. The light would come on. So that's a way to take a look at this one. How you feeling about the second one? I get that one right? Everybody feel good about it? Scale 1 to 10? Yeah, 1 to 10, yeah. Okay, just review, I know. People, like I said, we usually do pretty good on this one. As far as quiz and stuff, because students usually kind of like the logic. All right, the not function. It's just an inverter, all right? So if something was 0, it becomes a 1. If something was 1, it becomes a 0. It's just the inversion of what was on the other side. That's what the not is, okay? Let's go down this. The circle indicates that the inversion of the logic has taken place. So this was a 1, this becomes a 0. If this was a 0, it becomes a 1. And a not A has a little line over the top of it. The bar across the top means that you're taking the inverse of the logic. And I guess the way that they're showing it here is that a normally closed push button becomes, kind of true. So even though you haven't pushed it, even though you haven't pushed it, the activation of it's 0, it's still passing a 1. So that's kind of showing the logical representation of this, that you haven't pushed it. So even though you haven't pushed it, it's going to return a 1 in there, and the light would be on. And that's kind of how we look at it, is for close contacts. The not function used in conjunction with an AND gate on a low pressure indicator. So you got something like the pressure switch is open. Well, that's not good. The pressure switch is open, which means, it's 0. We invert it and we get a 1. So if you turn the power on, you get a 1 and a 1. The low pressure indicator light comes on. So we've inverted the situation where the pressure switch was open. When the pressure switch finally does close, it becomes false. And so you got a 1 and a 0 and the light goes off. So that's kind of a not truth table. Here's a NOR function. Let me do that. Sorry, not truth table, NAND function. So the NAND gate inverts the output. So normally an AND was you needed A and B. You needed a 1 and a 1 to get a 1. But we inverted it. So the 1 and the 1 actually gives us the 0. Same thing, normally on the AND, if you just push one of these, nothing happens. But because it's inverted, the 0 becomes a 1. And so that's what the NAND is. It is inverting. And that's the same with the NOR. Normally, if you pushed A or B, you would get this to come on. Well, it's not happening. When you're not pushing this and you're not pushing this, you got zeros inverted to 1. So the NOR is inverted. And once again, that's when we talked about a lot of our not logic. Okay. So if we take a look at some 3 and 4 examples, I got my paper here. PB1 and PB2. Okay, so I'm going to come over here. I'm going to go with a PB1 and a PB2. Okay, and then or PB2. Oh, I'm doing the wrong one. Where did that one? Sorry. That's too easy. Sorry. Let's try this again. I got PB1 and PB2. Let's try that again. PB1 and PB2 turns on light 1. Okay. PB3 turns off light 1. So I'm going to do an and here. And here's light 1. I'm going to do a PB3 right here. PB3. So let's see what this means. Notice I got a not right here. So this is an and. I need a 1 here and a 1 here in order for that to come on. So PB3. If I'm not pushing it, I got 0 over here inverted to a 1. So if I push PB3, that 1 becomes a 0. And if this was on, it would be going off. So I got a PB1 and 2, a 1 and a 1 would give me a 1. So 1, 1. Push the button, 0, it goes off. All right, everybody feel all right on a scale of 1 to 10 about the inverted PB here to turn it off? And you start thinking about like how's that look for a normally closed button, right? And then we have the fourth one too. Let me see what the fourth one was. I think this is this one, yeah. Hang on. PB1 and PB2. PB1 and PB2 turns on light 1. PB3 and PB4 turns off light 1. There's my light 1. PB1 and 2. 1, 1. Give me a 1 here. But now I've got 3 and 4 turns it off. So if I got my not right here, I got PB3, PB4. Okay. So if I want this light on, because these are ands, I need 1 and 1 right here. Push this, 1 and 1 gives me a 1. I need 3 and 4 to turn it off. So because this is an and right here, I would need to push this and this to give me a 1, which would be inverted to a 0, and it would go off. Okay? Now, if you have 2 ands in series like that with nothing in their way, you can simplify this to PB1, PB2, not PB3, and PB4. Turns on light 1. You can make it all a big gate, a single gate, because you still need to push this and this. And remember, this is always going to be 1. If this was 1 and this was 0, I got nothing. If I make this a 1 and a 1, this becomes 1 inverted to 0. All right. Scale of 1 to 10 on that one. How we doing? All right. Seems simple, huh? All right. You guys are doing good. The exclusive OR. Piece of paper. Get another paper. The exclusive OR means that we're truly looking for an OR. And that's what we had before, 0 or 1, 1 or 0. They return the ones. In a typical OR, a 1 and a 1 would give us a 1. But we are looking truly for an OR. Okay? We don't really use this that much right now, but someday we will. And that's just going to look a little bit different. We're not going to need to know this for our lab. NAND NORs, where's that at? NAND NOR logic. Let me see where we're at. What number is that? Oh yeah, hang on. Find a piece of paper. Get a piece of paper, hang on. I believe it's this one right here. All right. PB1 or PB2. There's my OR. PB1 or PB2 and PB3. Here's my PB3. Turn on light 1. PB4 or 5 turns it off. So I've got PB 4 or PB5 is going to turn this off. So once again, I'm going to take PB4 or 5. And that would turn it off. So this would return a 1. I probably need a not right there. So let's see. 1 or 2. So if I get a 1 here, either one of them, I get a 1, I'd get a 1 here. And I push this button 1, I get a 1 here. And right now, this is 0 because I haven't pushed anything. So it gets inverted to a 1. So if I push either one of these, I get a 1 in there. This would go to 1 and it would go to a 0. So you just got to kind of keep building them up in your head just to think about, you know, what if I push the button? What's going to open? What's going to close? And the thing is, if you were programming this in ladder logic, you still need to kind of build it up in your head and look at the logic and say, all right, if I push this button, what's opening, what's closing, what's opening, okay? So it just, and the other thing is you could look at it on the screen. When you program Boolean, you'll see what's coming true, what's green, and what's not, all right? That's the beauty of it. All right. The mathematical study of binary number is called Boolean algebra. Boolean algebra is used to write the combinations. And so we went from the pictorial, we learned ladder. We now went over the pictorial version of this. And now we're going to go over the Boolean algebra of it. And here's the little cheat sheet. So the ands means you multiply something. That's how somehow you got to get that in your mind. That if you're doing the and, it gets multiplied. If you're doing the or, it gets added. And then we already said the not has just got the line over the top of it. So the or is plus. And here's your little cheat sheet right here. I said the and is multiply. So A and B, when you put them together like that, that means multiply, A times B. If it's an and, you put the line over the top of it. It's inverted. The or, I said you add the items on the end here. If it was a 3-gate ABC, it'd be A plus B plus C. The nor, you just put the line over the top of it. It means it's inverted. And there's my logical statement, not there. Okay? So you can check it. And you multiply them, AB. And then or means add plus C. There's AB plus C. Here's your NAND. So it's AB with a line over it. And then plus C. So not AB plus C. Or is the plus. A or B, which is A plus B. And it's going to be multiplied by C. Because and means multiply. Notice you put them in parentheses there. And once again, the nor is just going to be an or because you're going to be adding them, A plus B, put the line over it. You need parentheses, multiplying by C. All right. So you just kind of got to work it through there. Now, a couple of things that, you know, some of these algebra laws do hold. A plus B is B plus A times B equals B times A. Your parentheses can work, you know, with adding and multiplying, but distributive law does not work here. Okay, that's why you got to be careful to keep your parentheses as the problem indicates that they should be. All right, determine logical and Boolean equivalent. Here we go. This is an or, so we're going to be adding them. A plus B. There's a C and a not D. So what is this going to be? This is just going to be all of them multiplied together. Remember, the first one has to be in parentheses. There it is. A plus B times C times D. You could, why didn't they put the A plus B first in parentheses? Yeah, they could have, because these laws still hold. As long as you put the parentheses, A plus B times C times not D, you're good to go. On a scale of 1 to 10, how does this one look to you guys? Pretty good, a lot of good ones. All right, all right, all right. What's this one? Determine the logic. Oh, this is interesting. You just got to follow lines, right? There's A not. There's B not. So we got this. This one right here means multiply. So you're multiplying the A not times the B. There it goes. There's multiplied. A not times B. This one is multiplied the A times the B not. This one means add them together, right? Or you add together. Not AB plus A not B. There it is right there. Algebra examples. What do we got? Let me see what I got going here. Hang on. All right. Create the ladder equivalence, it says. All right. A plus B, C. Okay. So remember, plus is or. So I got A or B times C is an and equals Y. That's what I got. A or B times C equals Y. That's what I got for that one right there. This one. A or B. Oops. A or B. And, which means the multiply means and C or D equals Y. Because the plus means or, A or B, C or D. Right there. Where's my paper here? I got AB, which is in series, A times B, or CD. Right? A or B, A times B, or C times D. And this one, A or B or C, but this is not A, B, C. That's the same as yours, I think. Not A, B, C. And not D, E equals Y. So the ones with the lines over them, they just become normally close contacts when you go into ladder logic. Okay, that's what I'm coming up with that one. So this is usually what people like the best, taking the algebra and changing it into ladder logic. Changing the ladder logic into algebra seems a little bit harder, but remember, it's all the same. You can take this and you can, changing this into pictorial is often a little bit difficult for people, but you know, it all moves around. It changes quite a bit. Okay, so there you go. All right. We'll just do a couple more, then I give guys just a little bit of break because we're getting there. Two limit switches are connected in series with each other and in parallel with a third limit switch. So here's what we've done. You learned relay schematics, logic. You learn how to convert it to ladder logic. It can be converted to gate logic. It can be converted to Boolean equation. You can go any direction with these. You know, you can jump from this one to this one, or this one to this one, or that one to that one. It's all the same thing. It's just, this is saying A and B. So these got to be multiplied together. There it is. A times B. The or is the plus. Plus C gives me Y. There you go. There's my gate logic right there. Okay. Scale of 1 to 10. Does this seem to make sense that these are all saying exactly the same thing? Okay, good. So we just got a few more. Why don't I give you guys all just a quick 5-minute break? I'm going to get some more water. I will come back here at 7:11. All right, I will stop sharing here. just take a quick 5 minutes. I want to get some more water, and then we'll finish this up. And then I'll answer any questions that you guys got. Okay. Sorry, guys. About 1 more minute, we'll roll. Sorry. I got to be 100% next time I see you guys on Thursday. That's what it is. There's too many conspiracy theories in the world these days. In my opinion, you come up with a conspiracy theory when your mind can't grasp reality. Mine is that cough drops actually have a chemical in them that prolongs your cold. How do you guys feel about that as a conspiracy theory, huh? Could be true, right? No comments on that one, huh? There you go. Fascinating. I know. Think about it. I don't know. I mean, makes you wonder. I mean, these are like Costco or something, man. I don't know. Like, I'll probably never heal up with these. All right, we're gonna roll again. We're gonna roll. I'm gonna go back to sharing my screen. And here we go. Before I get going again, I want to verify that you can see my PowerPoint. You guys can hear me. Yep. There's anybody else? Okay. Let's knock her down. So once again, going between them all, you can do them all. Here's limit switches. You got a big and or, couple in series in parallel. That's what the ladder looks like. So you're going to be multiplying the top rung together, multiplying the bottom rung together. That's what this is showing. There's an and and an and. There's a multiply and a multiply. And then you just add them together to get the Boolean. And there's the graphic version of it. A few more. What's this one? This is A or B. It looks a little bit different on the ladder here. That's the problem. But then what? You'll see that Siemens looks a little bit more like this compared to Allen Bradley. But once again, it's A or B, and that is in series with C or D. So A plus B or C plus D. So once again, there's you get all these are just equivalent, one way or the other. Everybody feel good about this one? Scale of 1 to 10. What do you think? Looks all right when you look at it. Maybe this looks a little bit weird over here, but that's this potential is the same. That's what you gotta recognize. What's this? Normally close. So there, you just got the PB depicted as a knot right there. Okay. A not B, multiply together. And that's the way that we're modeling this. Okay. This is the output of lamp is on. So you got, oh, this is interesting. A not B, not A B. So once again, these two are going to be multiplied together. And then they're added to these multiplied together. And once again, this is exclusive. We're not going to worry about this. But the gate logic, and you can follow it. This is going to be A not B. There you go, A not B. And that's what it's showing here. A not B. And not A B. The other one. All right. Any hard ones here? Oh, here's the one we got to talk about. Yes, here you go. This is a two stops, 2 start station memory circuit. That's what this is showing here. So you got C and D, and you got this and all of this right here. So you got, you know, this and this. In what's interesting is this is the big OR right here. Okay, and that's what my showing. This is my OR right here. So I got this and the OR. Okay, stop, and the OR. Now the OR includes the memory contact here. So on some Boolean, you can just draw that around like this and then feed it right back into itself, because the output is an input. So here they're taking the output and they're wrapping it around as an input. On Siemens, you can't do this. On Siemens, you just put the address right there. It won't wrap around. You just take the output and you put it in there as an input, and then it would work. So if you have a memory situation like that, it's just, you don't draw the line. You just put that value in there. Hopefully that makes sense. How does this look? This memory circuit, scale of 1 to 10. That seems like it's making sense to you guys. All right, we'll be doing some things like that. It says quiz and lab. I'm just going to show you one other thing real quick. I'm gonna come right here. Can I just delete all this? Delete. Now just get down here and just delete. Okay. So now I've still got my program here where I created my tag table. And if I go into my main here, it says switch programming language. Here would be structured text, STL, but we don't have the right firmware in there. There's ladder, and here's function block programming, okay? So when you do function block programming, your instruction set changes. And if you hover over them, it says and, okay? And so if I want an and, I can just drag that in there, and it shows me an and. And what would my and be? Once again, if I just type switch 1, because I already generated it. If I came here and typed switch 2, I generated it. And then if I came here, I need to get an output on there. My output is right here. My assignment, I would set that there. And I could do my light 1, okay? And that's an and. If I go ahead and I download it, and there's an online edit, and let's see if it works. Okay, did it do it? What happened? Oh, eyeglasses. Let's try it. So supposedly, if I hit switch 1, see, I'm clicking switch 1 and it's going true to false. So it does monitor it. And I'm switching 2, going true to false, and it's on. If I come and look here, here's switch 1. I'm going to click the second switch and see if I get my output. I got my input and I got my output. So it looks like it's working. It's the same, you know, kind of online monitoring that I'm encouraging you to do. To look, say, okay, this is on. How come this isn't on? Oh, because it's an and. They both got to be on. And then bang, I got logic. All right. So that is, you're going to be generating some Boolean solutions on this one. Okay. It says quiz then lab. Let me stop sharing. I know it was a short one. These first couple Siemens aren't bad. I want you to get your mind around it, get a grasp of it. Because when we start function block programming, it gets gnarly. All right. So I encourage you to still take a look at the lab. Be sure you're ready to go when you get here and knock it down. I'll be there about my normal time on Friday, about 5 o'clock. What questions do you have for me? Or on Thursday at 5 o'clock? What questions you got? If you don't have any questions, the quiz is open. You can go take a quiz. You should be able to find it. You can sign off. I'll stop recording, but I'll stick around for questions.